time we were talking about connectedness, and we showed that intervals are connected, and I did an example to show that when you use the theorem that the continuous image of connected sets are connected, you can also show that the circle is connected. Now there's a related concept that's useful, and this is definition 2.5. It says the following: a metric space XD is path connected if given 2 points x0 and x1 in X, there is a continuous function f from the unit interval into X. So f of 0 is x0, and f of 1 is equal to x1. So the picture that goes along with this is x1 and x2. This continuous function from the unit interval into X really defines a path that joins x1 to x2. So who knows where it goes, but it might go around like this. X0 to x1. So this is path connected or pathwise connected, and the advantage of this is that it does imply that the space is connected. So XD is path connected, then XD is connected. So it's a stronger concept than just being connected, and the proof is by contradiction. Suppose it's not true. Then XD is path connected but not connected. Now remember what connected was. It said that you could not break the space into two disjoint open sets that were both non-empty. So if it's not connected, then we can write X as U union V, where that being so, since they're non-empty, we can take a point in U and a point in V. So let's take a point x0 in U and x1 in V. Since the space is path connected, we can connect them with a path continuous function f from the unit interval over to x with f of 0 equals x0 and f of 1 equals x1. Now remember that we proved that intervals on the real line are connected, and so by continuity f to the minus 1 of u, which I'll call u1, and v1, which is f to the minus 1 of v, are open sets in the interval 0, 1. Now the point 0, since f takes it to x0, which is in u, it must be in the inverse image of u. So 0 is in f to the minus 1 of u, which is u1, and 1 is in f to the minus 1 v, which is v1. So therefore, u1 and v1 are non-empty. Since every point in the unit interval gets taken to some point in x, every point must either be in the inverse image of u or the inverse image of v. So we also have the unit interval is the inverse image of u union the inverse image of v, which is u1 union v1. The reason we have equality there is if I start with any point in the unit interval and apply f, I end up somewhere in x. That point in x is either in u or in v. And so the original point is either in the inverse image of u or in the inverse image of v. Now, if you have two disjoint sets in the range, namely u and v, there cannot be any point that maps into both of them under f. And consequently, we also have that u1 intersect v1 is the empty set. But now let's see what we've done. We've managed to write the unit interval as a disjoint union of non-empty open sets. This contradicts the fact that the unit interval is connected. this shows that being path connected is stronger than being connected, or at least as strong, because it implies connectedness. And generally, this is a much easier thing to apply than trying to see whether a set can be decomposed as two open sets. So, for example, what about the disk in R2? So, X is a set of points X, Y in R2 such that X squared plus Y squared is less than or equal to 1. Is that connected? Well, pretty clearly, yes, because given any 2 points, x0, x1, the line joining them is going to be entirely within the disk. So, these can be joined by a line in the set. So that will give us a continuous path from x0 to x1. So it is path connected. Same kind of thing, for example, if we took the annulus, which is a set of pairs xy with the property that R1 is less than or equal, R1 squared is less than or equal to x squared plus y squared is less than or equal to R2 squared. So we have 2 circles of radius R1 and R2, and the annulus is everything in between. This is a connected set because given any 2 points, sometimes these paths are easier to draw than write down analytically. Suppose I have a point there and a point there. How can I connect them with a path? Well, I can simply follow the circle that x0 is on. I can come around like this until I'm on the same radius with x1, and then I can come in like that. So that would give me a continuous path in the annulus that will connect any 2 points. Now the third example is an example to show that although path connected implies connected, it doesn't necessarily work the other way around. So connected does not imply path connected. A lot of the time it does, and so it has to be a rather strange example to get this. So what we do is the following. Take x to be the graph of sine of 1 over x together with the y-axis. So it's all the ups and downs of the curve plus the y-axis.
What's the domain of it?
Second?
What's the domain? Because sine of 1 over x is not defined for x equals 0.
Right, so it's this is for x not equal to 0. So that gives me a certain set in the plane, which is the graph, and then I include the y-axis. So this is not path connected. That point there is, say, that could be, say, the point 20 pi. So we cannot get a continuous path from the point 20 pi 0.
It should be 1 over a multiple.
Yes, thank you. That will make the sign 0 to the origin, because the only way it could go is to follow the graph of sine 1 over x and eventually end up at 0. But that would say that we had a continuous extension of the sine 1 over x function to include the point 0, which is impossible because we can get subsequences that converge to anything between -1 and 1. On the other hand, if we could write the set as the disjoint union of non-empty open sets, U and V, well, one of them would contain the origin. Let's say for definiteness that it's U. But if you have an open set containing the origin, then it's going to contain points on the y-axis and points on the graph of sine 1 over x. and on the y-axis. And then the restrictions of u and v restricted to these subsets will disconnect at least one of them. So I'm missing out some details here, but basically if you could decompose the full set as union of two disjoint open sets, then since one of them contains the origin, if there was a point in the y-axis that was in V, then we would be disconnecting the y-axis, and if there was a point on the graph that was in V, then we would be disconnecting the sine 1 over x curve. But individually, these are connected. So you have two connected things that come arbitrarily close, and that makes them connected, but not, in this case, pathwise connected.
If you remove the point of the origin, are they still connected?
Are they? Yes.
Oh.
Because anything between -1 and 1, I could use the same argument on any point in that interval, because I can't draw it, but the sine 1 over x curve goes up and down like this, arbitrarily closely to the y-axis. And therefore, any open set that contained that point would eventually intersect with one of the ups and downs. So it would contain points from the graph and also points from the y-axis.
Can you explain the sequence thing that you used to show it's not path connected?
Right, if it were, the only way you can get a path from over here to the origin is you're going to have to follow the graph of sine 1 over x and somehow arrive at 0. But that involves getting onto the y-axis. And I have to do that in a continuous manner. And so I would have a continuous path that would take me to the y-axis. Now, if I could do that, then basically I would have extended the definition of sine 1 over x to have it continuous on a closed interval including 0. But since it has no limit as x approaches 0, I cannot do that.
And the way you show that is by taking subsequences along any horizontal line.
Right. So if there were some way of assigning a value at 0 in a continuous manner for the sine 1 over x function, then I could take the subsequence that came along the top of the humps, and I would tend to +1. Or I could take the subsequence that comes along the bottom of the humps, and that would tend to -1. And so it's impossible to have a single value there that will make it continuous. Is that all right? Anyway, that I think is the simplest example that I know of something that is connected but not path connected. So it has to be rather strange in order to achieve this. we're on that topic, let's have a look at a situation where the two are the same. So in R2, let U be an open set. And then if U is connected, then it is path connected. So here the implication goes in the other direction. We know that path connected implies connected all the time. And basically this is avoiding the topological properties of that last example with the sine 1 over x graph. If you have a nicer set, an open set, then the two concepts are the same. So to see this, let V, let's fix a point x0 in U. And let V be the set of points in U that can be connected to x0 by a path. And let W be the set, basically the opposite, of points in U that cannot be connected by a path to x0. So clearly, V intersect W is empty because either you can be connected to x0 by a path or you cannot. It cannot be both. So I claim that V is open So first of all, let's observe that V is non-empty because there exists a neighborhood of some radius delta centered at x0, which is contained in U, because U is an open subset of the plane. By the way, there's going to be nothing special about the plane here. This could work in any Euclidean space. Now, this is just a disk centered at x0, and so you can just take a straight line radius from x0 out to any point. So all points and therefore V is non-empty.
Is a point path connected to itself?
Yes, I could take the constant function f of t is equal to f0. So that is a continuous function that sends 0 to x0 and 1 to x0. So sort of a degenerate case. Now, I have to show that V is open, so let x1 be a point in V. By openness of U, I can find a ball centered at x1. So there exists an epsilon greater than 0 with the neighborhood centered at x1 and radius epsilon is contained in the open set V. So here's the picture. Here's U. Here was my original point x0. Here's x1. And now I have a ball centered at x1 of radius epsilon that's completely contained in U. Now, since the point x1 is in V, that means I can get a path from x0 to x1. And then from x1, I can go on to any point in that small ball. So if I have here, say, an x2, then by going first to x1 and then out of radius, I can arrive at x2.
So we're given that x2 is the V, right?
Right, I'm about to say that. So for any... Right, we're given that x1 is in V, and now I'm looking at a sufficiently small neighborhood that lives entirely inside U, and so for any x2 in this neighborhood, we can get a path that goes first of all from x0 over to x1 and then on to x2. And consequently, this neighborhood centered at x1 lives inside V. So any point in V has a sufficiently small neighborhood that's also in V. Therefore, V is open. Now, what about W, the ones you cannot get to by following a path? Well, it's basically the same argument. So I now claim that W is open. So if I have a point in W, then there is a neighborhood of that point of some radius, say alpha, centered at x1 that's contained in U. So again, here's U. x0 x0 is over here, then I have a point x1 that I cannot reach by following a path, and I now have a neighborhood of x1. So I think you can see that if I could follow a path from x0 to any point inside that ball, I could then travel inside the ball to the center x1. So if I had an x2 in here, and if I could get a path from x0 to x2, then I can just come straight down a radius and arrive at x1. So no point in this neighborhood can be connected to x0 by a path since we would then get one to x1. So if you have a point in W that cannot be connected to x0, then everything in a small ball around it also cannot be connected to x0. And therefore W is open. So we've arrived at the situation of two open sets, V and W, that make up the whole of U, because either you can or you cannot find a path connecting x0 to any given point. So if we're assuming that U is connected, since U is connected, either V or W is empty. But we've already seen that V has points in it. Since V is non-empty, W must be the empty set. W is the set of all points that you cannot reach with a path from x0.
So x0 isn't in W?
No, that one's in V. Because we fixed x0 and then we said let V be all the points that you can reach by following a path from x0. Okay? So what we've shown is that W being empty means that there is no point in U that you cannot get to by following a path. And therefore, every point can be reached by a path. So therefore, U is path connected. So here's a situation where the implication goes in the other direction. If you have a connected set, then it is path connected. But you need some extra hypothesis, and in this case, the openness of the set is what is needed. So it gives you just a little bit of extra room for constructing the paths.
And where did we use the fact like that we're using a metric space R2? I mean, it's pretty generalized, right?
Yes, it's pretty general. Where we're using it is because we know what balls are.
So you have local path connectedness.
Yeah, it's locally path connected. So what that means is that in a ball in this metric space, and this could be R2 or Rn, any point in the ball can be connected to any other point in the ball. Now in a general metric space, this could fail because you don't really know what the balls look like. But in Rn, you do know what